Hello and welcome to the lecture Sequential Modeling Part 2. In this lecture, we are trying to understand sequence to sequence modeling. Then we introduce a concept called attention, and then we learn how to compute attention through recurrent neural network. So we going to start a very interesting topic that is called sequence to sequence modeling, using whatever we have discussed, our sequential model, RNN or LSTM. Now, as we know that this RNN and LSTMs have been used for modeling the sequential data. But in sequence to sequence model, basically employ a encoder decoder model, what we have seen in the last class also. So sequence to sequence task relies on encoder decoder architecture, like this particular, if you see this particular image here, that you can see here that there is the encoder part. That means there is some input sequence is coming. Then this input sequence are basically extract the meaning of this input sequence. It's extracted as a context, which is go to the decoder part. This is the decoder sequence. This is another RNN or LSTM, and this will generate the output. Okay. So this is the basic architecture of encoder decoder architecture for sequence to sequence. So in this setup, encoder's final hidden state, and that means this, serves as a context vector, and that is very important in our discussion, or specifically today's discussion. We try to understand what do we mean by context and how it basically useful for this kind of sequence to sequence modeling. This context vector is passed directly to the decoder to derive or the drive generation. Now the idea is of this sequence to sequence modeling is basically used for, there is a sequence is given in Hindi and we translate it into another language like English. So it may be a machine translation kind of task. Okay. When we come to the vision, this kind of translation will come in that different aspect of kind of video frame leveling, frame level leveling kind of thing. Okay. So let's see that how basically our RNN LSTM encoder decoder model is doing this particular job. In this RNN LSTM encoder decoder model, each hidden state, so these are the hidden state, access the current input. Look, these are the current input, as well as the information all previously processed inputs. This is in this particular hidden state, which is input from previous layer and as input from the current input. So the two inputs are basically, as if this is a normal in any RNN LSTM thing. So as the sequence processed information from S0 to ST1, so this S0 to ST-1 is carried forward in a compressed representative within the hidden state at time state t. So after this step t, kind of the time instance, t time instance, this basically this compressed representation of input is called the context. Consequently, the encoder final hidden state, known as context vector, that is context vector, is expected to capture the essential information on the entire input sequence. So context vector is very important as output of entire input after the final state, and it basically expected to capture the essential information of the entire input sequence. For a very simplistic thing, what is the meaning of sentence? Knowing the meaning of sentence, we want to derive the sentence in another language. Okay, so this context vector is then passed to decoder to generate the output sequence. So this is the basic idea of sequence to sequence modeling. Now, what is the problem with this approach? The RNN LSTM encoder decoder model compress the entire source sequence into a fixed length context vector. That is a fixed length context vector before passing into decoder, that we have seen. Now, there is the information bottleneck. That means all the relevant information must be encoded into a single vector. That always may not be possible, particularly if this sentence is 2. This is only 4-word sentence. But if there is a 10, 15, 20 words sentence, then it is tough to get a very compressed or abstract representation which essentially contain all the relevant information. And that creates the information bottleneck. Consequently, the model struggles to handle long or complex input sequence, especially those longer than the sequences seen during the training. So this is the basic problem, one of the problem of this kind of approach. The limited capacity of context vector can lead to a loss of important information. Since it's a very compressed representation, it may lose some information, important information. Furthermore, the decoder must generate the entire output sequence using only this single context vector, because in the decoder side, the whole input sequence is basically given in this small context vector from which it generates. So maybe the decoder must generate the entire output sequence only the single, making it difficult to accurately recover all the information from the source sequence. So there is an information gap, there may be between these, because in between is a very abstract or very compressed representation of the input sequence. As a result, model's performance often degrades for long sequence and complex translation tasks. So when model transfer degrades, this problem is basically with this RNN or LSTM in this way complex. So to mitigate the problems of context-based sequence to sequence model, we are going to introduce another very interesting concept called attention. The attention mechanism basically enables the decoder to consider all encoder hidden state when generating each output, rather than relying on a single fixed context vector, as we done in the normal encoder decoder architecture. So what actually want to say? We want to say that in our normal architecture, that is vanilla RNN encoder decoder model. So the last step, the context, and this context is coming as age, and decoder is doing from the single context vector. But in attention mechanism, it is doing in a bit different way. What it is doing? Now, attention, linear sum, is not coming from the only HT or final encoder state. Rather, H0, H1, H2 up to HT, all hidden state output is coming here to get this attention. And then in the decoder state also, this attention is coming here H0 as H1 and in this. So there, this attention is basically is coming from all the hidden state output of encoder, and when it is being derived, it is input to the all the decoder state. Details thing we'll see later. So this is the basic idea of attention. Now it is different from the context-based model. This is attention-based RNN encoder decoder model. Now let us try to understand what is attention. The attention mechanism enhances the RNN LSTM model by enabling it selectively focus on most relevant information within the sequence. Now, given a sequence, let's say a sentence, it's a sequence of words. Now, all these words are not equally important. some word is more important than other words. So attention is try to get some score-based mechanism that this word is more important, the score may be high. This is a very hypothetical explanation, and the other words is not that much high, so that much important, so less score. Again, some word there is some high score was this important, some similar. So it selectively focus on the most relevant information within the sequence. In conventional LSTM, what we have in context-based model, information from sequential inputs is encoded into hidden state, and the model may struggle to preserve and effectively utilize the important information when processing long sequences, as we have understood for the context-based RNN LSTM sequence-to-sequence model. But in case of attention mechanism, which address this limitation by assigning a learned attention weight to each LSTM hidden state. Now, attention weight. So which word or which state of the LSTM, that means particular word in a sentence, is more important according to its relevance to the current prediction, and that is very important. Given a particular word to predict, we have to find out which of the previous words is more influencing, more important, more relevant. So that is being learned by this attention mechanism. These weights are typically computed using a scoring function that was followed by a softmax operation, producing the normalized importance values across the sequence. So this is the attention mechanism which is being employed in case of sequence to sequence model in place of simple context based modeling. Okay. So a context vector is then generated as the weighted sum of LSTM hidden state that we have shown here, that this is the weighted sum of encoder hidden state like this. Detailed thing will come later, but this is a weighted sum. Okay. Now allowing the weighted sum allowing the model to emphasize the informative time step while reducing the influence of irrelevant ones. So informative time steps we have to emphasize and reduce the influence of irrelevant ones. So we dynamically selecting relevant temporal features. Attention improves the ability of RNN-LSTM model to capture long-term dependencies more efficiently, enhance the feature representation, and improve prediction accuracy, particularly for long and complex sequential data. So this is the basic advantage of attention-based sequence-to-sequence model over the context-based sequence-to-sequence model. Okay. Now we try to understand what is the problem of context-based model once again. In conventional sequence-to-sequence model, encoder processes the entire input sequence and complex in a single fixed time that we have discussed earlier, which is then used by the decoder to generate the output sequence. Now, what is the problem of this? This fixed length representation creates a significant information bottleneck. That this is a small context vector that may not contain all relevant information from the input sequence, particularly if input sequence is very large and complex, when the sequence is long and complex dependencies. As the sequence length increases, the context vector may fail to preserve all this relevant information, resulting in information loss and reduced performance that we have just discussed. Furthermore, the decoder has access to the same compressed representation at every decoding step and cannot directly identify which part of the input are most relevant to the current output. So decoder also have less information on this, that which part of the input sentence is more relevant than others. In this position, attention comes to mitigate this issue. Attention mechanism address this limitation by allowing the decoder to dynamically access all encoder hidden state rather than relying solely on a single context that we have shown here in this. It is all hidden state and it is coming all. At each decoding step, attention calculate relevant score for the encoder hidden state, convert these scores into normalized attention weights, and compute the weighted sum of generate step-specific context vector. So that every step the context vector is different. Again, I repeat it. At each decoding step, attention calculates the relevance score, that relevance of a particular word being calculated for the encoder hidden state, because each encoder hidden state is model one word, converts these scores into normalized attention weights, normalize it to get the attention, and computes the weighted sum to generate a step-specific context vector. So what is the consequence? Consequently, decoder can focus different portion of the input signal when generating different output tokens. That is very important. When you generating output, a particular word is very important. When is the next token, other word is important. That can be done by the attention. This reduces the information bottleneck, improves the handling the long sequence and long-term dependencies, and enables the model to align relevant input-output elements. So that is the main advantage of attention over the normal context-based sequence model. Thus, attention transforms the fixed context sequence architecture into a more flexible model capable of selectively retrieving the information required for each decoding step. So that is the most important thing. It selectively retrieve the information required for each word at the decoding when generating the decoding sequence or output sequence. Now, the most important question, how we compute the attention or context vector using attention. So the main question is coming, how does it decide which states are more or less useful for every prediction at every time step of decoder? So that is the main important aspect. Here in this picture, we are trying to demonstrate it, that how actually it is being done. Now, use a neural network to learn which hidden encoder state to attend and by how much. Okay. So first, compute the alignment score. So what is alignment score? That this is basically a kind of f of attention. Okay. So this is a kind of function. It is coming s of t minus 1 and this hi. This is called the alignment score e of t of I. Okay. So this is called the alignment score. Now, then what we are going to do? We normalize this score using the softmax. We are using the softmax. So this is a neural net, and this hi is coming from the encoder. You see, hi is coming from h0, h1, h2, h3, h4. So it is coming from here, and this h0 is coming from this the decoder side, and from these two we'll find this, and then we put the softmax, which is given the alpha t of I, that is normalized. Now the context vector is computed. It's linear combination of this hidden state. So this is the context vector Ct, and this C1, C2, C0. Ct is equal to I is equal to 1 to k alpha tk into hk. So this hk is basically from here is hk and this. Now this context vector using decoder, that st that is every decoder is YT minus 1. So this is coming here, ST minus 1 and CT. So this is the basic understanding of that how actually the this. So we go step by step that you can understand it properly. So first iteration. So first iteration is that this is the only first step. For example, RNA system with 4 states will take. It takes both encoder and decoder. In the first iteration, S0, H1, H2, H3, H4, because S0 is only available, and H1, H2, H3, H4 available. Input is F attention, F of attention. Alpha I, 1I, and C1 are the obtained. So first we compute EI, comma. This is F of attention. This we put it in the softmax, we get this alpha II. So for 1 it's 1 1 1 2 1 3 1. Now the context vector is computed, that C1 is computed 1 to T alpha IK, what is equal. Now this context vector used S1 because this is S1, decoder Y0, this is basically coming from this side, from here it is Y0, and S0, this is S0 and C1. This is the first step. What is the next step? The next step is same, is that in second iteration S1, now only this difference is S1 is coming, H1, H2, H3, H4. So this is the, so S1 is coming. We get this EI as an alignment score, E of 2I at F of the S1 and HI. HI means all 1, 2, 3, 4. Normalize this score using softmax. So alpha I 2, 1, 2, 2, 2, 3, 2, 4. So alpha 2I is softmax this. A context vector is we sum it up over it, this I2k, alpha 2k and hk, that is multiplied this hk, and context vector is decoded. The C2 is coming, that S2 is how it is coming, that decoder Y1, this is Y1 is coming, and S1, this S1 is coming, and C2 this is coming. So this is second step. Third step is very similar, is that E31 3I is how it numerated. It is being that S2, that is 2 is coming, H1, H2, H3, H4, this HI is coming, normalize alpha of 3I in softmax of 3I. So this we can get this 3 1 3 2 3 3 3 4 of alpha 3 1 alpha 3 2 such on. Now we context vector compute as linear sum, as you can see the summation can t is equal to 4 and alpha 3k into hk, and the context vector is S3, and decoded how it is. S3 is how, got a Y2 S2 and C3, Y2 S2 and C3, and this is so, and same thing iteration 4, same mechanism. So we are not going to. So here also E4I is equal to S3HI is, and alpha 4 is softmax, C4 is taken as similar, S4 is Y3, it is Y3, then S3 is S3 and C4. So what is important here, that every decoder step we are generate this attention for this H1, H2, H3 and the corresponding S3 and the previous output. So that for a particular word when predicting it, try to understand, try to model which of the word here is more important for this particular word to predict, and that is the major contribution, major advantage attention based context generation. So in summary, in this lecture we discuss sequence to sequence modeling. We particularly introduce attention, and then we try to understand how compute attention through RNN sequence to sequence modeling. In the next lecture, start a new topic, the generative AI for patient task. Thank you very much.